Let's talk about BLT, or in other words, what I had for lunch. So this is Byte Latent Transformer, and basically the main idea is let's not use tokens and let's for a LLM, and instead let's kind of have the model do this dynamic tokenization procedure, which they call patches. I wanted to talk about this sooner, but I had finals, so it's a little later. The video is a little later than what I hoped for, but better now than later, I suppose. Better now than never. So, yeah, I think it is an interesting architecture. It's very much an engineering, like engineering paper. They do a lot of things to get it to work. So, I've heard like, oh, this is the end of tokenization. No, I mean, it's a good first step, but there's a lot of engineering that goes into kind of making it work in the first place. Like, it's not like an LLM tokenization is easy. You just bam, lookup table, done. This is not trivial. So, yeah, let's just start. So like everyone knows normal tokenization, and specifically like I don't know what's used now, like byte pair encoding or something like that. Some tokenization procedures similar to that. But basically, if I have a set of words, I just have a ton of words and I want to tokenize it somehow. So I have like the cat sat on the mat. So what I can do is I can say, okay, so I'm just going to take every character and I'm going to convert that to a token itself. So I'll say the character T represents token 1, the token H or letter H represents token 2, E represents token 3, space represents token 4, and I just do this for my entire vocabulary. So you basically have one, well, let's do this in terms of ASCII. So you basically have one token for every character. So I don't know, is ASCII 256 or something like that? Basically, this is byte encoding because you're just encoding this byte representation of the character to a integer, which can then be tokenized because you have a vector and you have a lookup table and you say, okay, so the letter T represents this vector and I'm going to use this vector in my LLM and so on. Now, the problem with this is it's not expressive and it creates super long sequences. Like the letter T in the is a lot different than the letter T in sat. Like they're just completely different because of the context surrounding them. And the transformer will figure that out, but still it's not that expressive. Now, on the other extreme, I can say this whole thing is my token and I'm going to send this through the transformer. And at this other extreme, basically this is useless and you don't need a model at all. So somewhere in between, you can say, okay, so maybe I can represent each word or like cut off by a space or something like that. And the current state of the art, like go-to technique is this thing called byte pair encoding. And basically like the idea, I mean, there's a lot of things on it out there if you're curious, but the main idea is like, oh, I have a set of words just that I'm going to train on. And I'm going to basically form like these prefix or these n-grams that are most common and use those as my tokens. So if we look at this sequence here, and let's say this is my entire dictionary that I'm going to train on, we can see the ending AT is like, so like if we start out as with our vocabulary is just all the letters. So like the cat, T is already there, space, S, O, I think that's M. I think that's it. This will be our vocabulary that we start off with, but then we say, okay, so there's an A and a T here, which is very common. So we're going to add that to our vocabulary. And you just keep on building this up by using the most common n-grams, and you keep on building this up. So like another common one would be like TH or something similar. And you build this up until you are satisfied with the number of tokens you have. And then you can tokenize this by saying, so if this was 0 and this was 1, this was 2, this is 3, then this would be 1, 2, this would be 1, 2, 3, something, something, or something, whatever C is, we'll make that 4. So whatever space is 4 and then 0 because that represents AT. Anyways, too much on tokenization. The problem with tokenization is it doesn't really have context of like what is this actual word itself. Like it knows that there is a vector that represents AT, but it doesn't know like that it is AT. All it sees is a vector of numbers that represents AT. We know that this is AT. It doesn't know that this is AT. So whenever it sees cat, it actually sees just 4 and 0. Just two discrete tokens. Like it doesn't see AT. So, and another problem is that like tokenization, like it adds a lot of these biases that forces the model to not handle character level edits. For example, if I wanted to, let's come up with a stupid edit. Let's say I wanted to add the letter Z after every letter A. It would be difficult for it to do that because it basically has to convert 4.0, whatever this is, cat 4.0, to something completely different. Let's say there was another token down here, which is AZT. It would basically convert 4.0 to 4.1 or something like that. So like it's very difficult for it to do that in general because of how we're tokenizing. Also, another thing that we want to do is basically dynamically allocate compute to harder and more difficult tokens. And I'll get into what they classify as harder and difficult in a second. But the idea is, if we look at the sentence, like if I have this prefix here, like the cat sat, and then I predict the letter O, like the letter N is pretty easy to predict if I give you this part of the sequence here. But let's say I give you, let's just say I give you the word the. Like it's pretty hard, and it's pretty hard to predict the word cat because there's so much uncertainty. It could be any word basically after the letter, or after the word Z, or after the word the. Sorry, I cannot talk. After the word the. So it can be any word. So there's very high uncertainty for the word, for the letter C versus like for the letter N over here. So you probably want to allocate more compute to the letter C rather than the same amount of compute everywhere. So dynamically allocating compute is kind of what we've been seeing, and it makes models better, but it also makes them more efficient whenever you're trying to do inference on models, because you're dynamically allocating this compute. Okay, so yeah, that's the problem with tokenization. There's a lot of problems with tokenization, but let's get into how they kind of want to form patches. So the idea of patching is we want to dynamically take a sequence and we want to basically form dynamic patches with them. So we want the model to kind of learn how to do this in a way and how to kind of manipulate it in a way. There are so many ways you can do this, but we'll just talk about the way they do it. So if we have the cat sat, actually I'll just show the example they have down here. So they have this over here, this sequence of words. And the idea is we want to take these bytes, which are just the characters in like the ASCII table, and you want to convert them to basically windows, which are going to be your patches. So like given this sequence here, we can say, let's form patches just by, like a trivial way to form patches, just to do it by space. So you could do, this is a patch, this is a patch, this is a patch, this is a patch, and so on. And then this would be patch 1, this would be patch 2, this would be 3 and 4. And then you could send this through your model in some way, and that would be your patchification. So that's one way they do it in the paper. That's like one of the trivial ways they mention. You can split it up using patches, or using spaces. Another way is you can say, I'm going to patchify this by patching every fourth character, which is also a trivial way. Now to get a little smarter with this, and to kind of bounce off the idea of like dynamic compute based off the character, they look at or they look at a bunch of sequences. They take a pre-trained LLM that's just trained to predict the next token, and they send this entire sequence through, and they basically have it predict the next token. So and the next token is the byte. So they train it on bytes, so just characters, and they have it predict the next byte in the sequence. So if we give it this entire sequence here, or rather this entire sequence that they have down here, it'll make the next prediction for the next byte. So if we give it D, it'll make the next prediction for A in this part of the sequence. Normal LLM behavior. So given this probability, we can calculate the entropy, and the entropy can tell us exactly how uncertain the model is. Real quick, we basically look at the entropy over the entire vocabulary, where the entropy looks like this. So if we have a probability of 0 or a probability of 1, that's low entropy because the model is like 100% certain, oh, this isn't the next token. Like I'm 100% certain that the next token is not the letter W, or I'm 100% certain the next letter is A. If it has 50% uncertainty for some token or some byte, then we can say there's high entropy because it's highly uncertain. So like at the beginning, there's this is the entropy right here. So of the next byte. So we can see that the entropy is very high for some of these bytes, while it's very low for others. Like this is very high entropy, this is very high entropy, and this is like almost 0 entropy. So we can see that the entropy changes a lot. And what they do is they basically say that a patch is going to be created every time we see a high entropy prediction, or every time we see the model be very uncertain about the next letter or the next byte. So here, very high uncertainty. This is a patch right here. Here, very high uncertainty. This is a patch. Very high uncertainty, patch, patch, patch. And then we start here, where this is going to be a patch all the way until we get to here. So this is going to be our first like actual patch here. And then we see it's a patch until we get to around, I think, here, and so on. So basically every time we see a high entropy byte, we're going to start creating a new patch until we see another high entropy byte. And we do that based off an LLM. And the intuition is that this LLM is going to kind of inform us. It's going to inform us how hard it is to predict this next byte. How much do we want our model to kind of be thinking about that byte? And this is how they do the patchification. Every time they see this high entropy byte, they create a new patch. So here's a bunch of patch strategies over here. This is forced-righted, so the trivial, every 4 bytes we're gonna create a patch. This byte pair encoding, this is kind of what I talked about earlier. You just do normal lookup table. Space, as self-explanatory, you just do it by every space. And then they have 2 entropy-based ones over here. They have one, which is every time they see high entropy, they create a new byte. So if we look down here, D was high entropy, so D is its own byte, A, E. And it doesn't start until we get to here, the letter N, where an actual byte starts to, or an actual patch starts to form. And then until we get to the letter N, we have this patch and so on. So you get something that looks like this, which, makes sense. Like if I were to give you this here, it would be pretty easy to predict maybe a Game of Thrones or something like that. So this is their patchification strategy. This dynamically allocates compute and basically batches together bytes that are easy to predict, given like one byte that is hard to predict. So that's kind of the intuition. Batch a bunch of easy bytes together that are kind of easy to predict, because they can all be one token. Like you don't need that much compute to predict these bytes. So they can just go in the same byte, or the same token rather. So just kind of batch them together. So now that we have this patching strategy, how do we use it? How do we use this patch strategy in an LLM? Like, I can't just throw this in an LLM because these are integers themselves. Like this, like these are letters, or these are yeah. This is just a patch of a sequence patch itself. Like, you can't just throw this in an LLM trivially. So that's where a lot of this paper kind of dives into. Assuming you can patch, which we now have a method to do so, using this entropy-based patchification, we can now encode these patches in some manner. So the way we're going to do that is by I actually have some diagrams I drew out for this. We're basically going to send our byte, we're going to tokenize our bytes, and then what we're going to do is we're going to basically distill the bytes and do patches based off the patchification strategy above right here. So like this is a sequence of bytes here, and we're going to distill these bytes into one single patch in some way. And then we're going to throw those through a transformer. And then we're going to have our model predict every byte in this sequence. So we're going to have a model that's predicting byte-wise. It's not going to predict patch-wise, it's predicting byte-wise. But we're going to have the model operate on the patches. So the model needs to predict every byte individually. You may be able to speed this up using something like speculative decoding. But for now, since this is kind of the first paper on this, you have a model that is predicting every byte individually. But it's going to operate patchwise. So that's the idea. Now, like I said, this is kind of an engineering paper, so there's a lot that goes into this. The first thing is we need to get these bytes some information about their surroundings. And note that all of these encodings are going to be causal, so we only look at the past, and that is so we can make these causal predictions, and so that we can train this efficiently. If you didn't make this a causal model, you wouldn't be able to train it efficiently at all. So this is a causal model. The first thing is we're going to take our bytes. So let's say we have the cat, where there's space in the middle, and we're going to encode these 2 bytes. These are not bytes, but pretend they are. Like, they're working with bytes, so 256 binary data. So you have 256 values. That would just be 8 binary values. And you're basically going to tokenize these like normal. So we have the word "the" and the word "cat." So if we treat every single one of these as like an integer representation to make it easy, then this would be 1, 2, 3, 4, 5, 6, and then 1 again, because this is the same byte as this one over here. So that gives you your sequence representation for the sequence of the cat. And then we do a normal lookup table. So this is just our tokenization here, where we take the integer representation and we tokenize it to some vector. So this translates it from a 256 one-hot vector, or rather, one-hot vector or a byte, to a actual embedding, which we can throw into a transformer. Now you can actually directly operate on these, however, these are not informed of their surroundings at all. And they find that it works better if you give it kind of this n-gram information. Let me go to that. So they have this n-gram information that they talk about down here. And the idea is we can take this, say, let's take token 4, and we can add some n-gram hashes to it. So they do that using this formula here. Basically, let's say we have our token, xi. I is the ith token in the sequence. X is our embedded form, and E is going to be our n-gram informed embedded form of the token. And what we can do is we can take several n-grams, and specifically they choose n-grams of size 3, 4, 5, 6, 7, and 8, and hash them. They do that using this hash function here. It doesn't really matter. Basically, you take an n-gram, and you're going to hash it, and then you're going to feed this through a lookup table, and then you're going to add that to your original embedding. So, for example, if I have if I take this one here, the fourth one, then I can take an n-gram of size 3 as these first 3 here. So it's going to be an n-gram of size 3 going back n-1. So this will be our n-gram here. We take that and we hash it. So we take the n-gram, it's going to go through this hash function, which gives you some integer value within your hash table size. And then you throw that through the hash table and you get some vector embedding for that hash. I don't think the details are too important for this. Basically, you're taking n-grams and you're hashing them. It's like a non-machine learning way to get these n-gram informed embeddings. So you just have a bunch of lookup tables where you're saying this one corresponds to the n-gram, 153. And this one corresponds to the n-gram 742. And these are just vectors of size of your embedding size. And you add them all up for all your n-gram sizes. So for 4, you would say, I'm just going to look at the n-gram by itself. Or I'm just going to look at the 1 gram. And then I'm going to look at 3, and maybe I look at 4, and so on. And then you just add all those embeddings together to get this n-grammed inform embedding, which is E sub I, and you average over all your n-grams that you're working with. So I'm curious if you can make this a machine learning method with a lookup table rather than like a normal hash table that uses a hash function. I don't know why they use a hash function, but they do. So that's going to be E sub I. Note the difference between E sub I and X. X is not n-grammed informed, E is n-grammed informed, but both are embeddings of our bytes. So now we have a sequence of n-grammed informed bytes. This will go into our transformer, and note that this is still just our byte sequence. Like, we don't have patches. So how do we patchify this? The way we patchify this is we're going to use cross attention to basically distill information from our bytes into these patches. So let's say we have this sequence here, the cat, and we have 3 patches that we want to distill it into. Let's say, so 3 patches, because let's say our original LLM entropy model said this is patch 1, so it would basically say this is high entropy, this is high entropy, and this is high entropy. So this is patch 1 here, this is patch 2, and this is patch 3. So this is just the number, these patches here just represent the number of patches that our entropy model said that we had in our sequence. Now, we basically start off with 2 sequences. We start off with one sequence, which is initialized to X. And X is our non-n-grammed informed byte sequence. These are our pure bytes. E, on the other hand, is our n-grammed informed bytes, and that is going to be used to initialize our patches here. And note that these are pooled, so this one here, P00, has to represent the word the, so it's going to be the pooled version of the n-grammed informed bytes of T, H, and E. Same for P01. It'll be the pooled version of this, so you can average them together or something like that. And same for AT for P02. And note that there is a K here. I don't think they actually mention K at all. They have it like somewhere. They have like K equals 2 or something somewhere. K is the number of patches you have per byte or per patch. That's weird to say. Basically, we have one patch we're going to create for the word the, and you can actually create 2 patches for that. So you're distilling the word the into one patch, but you can increase k to equal to 2. So then we would have a double OR sequence, and instead of distilling your sequence into one patch, you're distilling the sequence into 2 patches. So P0 would go into 2 patches, P1 would go into 2, and P2 would go into 2. So that's just what K is equal to 2 means. And you can increase this for whatever size. I'm going to be using K equals 1 because it's easy to draw. So now that we have our initial sequence and we have our patch sequence that we're ready to distill in, this is E, we can start distilling. So they call this the encoder because we're encoding the information into patches. We're creating patches. Now, the way you do this encoding is through cross-attention. Note that this is cross-attention. It's not a transformer block, it's cross-attention. You don't have anything fancy. There's a difference between the two. Transformers have feed forward, they have the residuals and norms and stuff like that. This is just cross-attention. So basically you do cross-attention where specifically these are your queries and these are your keys and values. And if you note the attention formula, softmax of QK transpose times V, you will note that Q is of shape N by D. I'm going to make the dimension the same. D by M and M by D. Where this part here is, this will result in a N by D output. So this part here is basically the structure of your output, Q. And this right here is kind of like the style, I guess you would call it. Kind of, you're sending information from K and V to Q. You're always sending information that way. You're always sending information from K and V to Q. That's what you're doing. So that's why you have K and V as your input sequence, your byte sequence, and Q as your output sequence, your pooled patches that you're distilling your information to. It sends information from K and V to Q. So cross attention does that by normal attention, just with K and V assists and Q assists. So the output is going to be, like I said, of shape of whatever the queries are. So basically this sends information from here to here. And this is going to be one updated representation of your patches. 2 things to note is that they have a skip connection around here, so you're modeling residuals rather than absolutes for attention, because that works way better. And another thing is they have prenorms on QK and V, and they have no positional encodings here. So this is just a direct feeding of information. Now in parallel, you have a transformer layer which operates directly on the bytes. Because if you just have these bytes, they're literally just the bytes themselves. So every transformer layer you add, you basically have a new representation of these bytes, which are now representations of interactions. And note that this has to be causal. You can't have this letter interact with this one over here. And this right here is one block. You basically have this transformer layer operating on your bytes to kind of update the representation in some way. And for your bytes, and this one here, which is taking the byte information and distilling it into your patches. And this is one block, and you stack this block. I don't know how many times they stack it, maybe 8 or something. I know they change it, they vary it, and they look at it. We'll look at what they do maybe later. But basically you take this and this is your block, so you stack it a few times. And this is your encoding. So your output will be an encoded representation of your bytes in some way, where the bytes are talking to each other, and sending information to your patches, where your patches are now byte-informed information. Now, you can't just have normal cross-attention. Like we have causal attention here, which is updating the byte information, so that's fine. But if you have normal cross-attention, you don't have causal information, which means you don't have this causality, which means you can't train the transformer, and you have to do it in a non-causal way, and it's not good because it's slow, and you can't train in a non-causal way because of that. So you can't just have normal cross-attention. What you have to do is you have to mask it in this way. So you only have inter-token communication for cross-attention. Sorry, I had to find it in the paper right here. They say we use a masking strategy specific to patching where each query only attends to the keys and values that correspond to the bytes in patch J. So intuitively, that makes a lot of sense. You keep this causal structure. So your attention matrix looks like this, where these are your queries, these are your keys, and basically you have your keys sending information to your queries in this way. So P1 is going to be a linear combination of all your keys, and P1 can only be a linear combination of the tokens and of the bytes for the word the, because you're distilling the into P1. Same for space C, you're distilling that into P2. So you only have this part of your mask unmasked for P2, so that's only a linear combination of spacing C. Same for P3, but for A and T. Yeah, so that's one note for cross-attention. Basically, you only want it to send information to the patch it's supposed to be distilling into. If you do 2 patches, so if you increase k equal to 2, you have a mask that looks like this. So like the first 2 tokens here would represent the word the in some way. This one and this one would represent space and C in some way, and this one would represent A and T in some way. Or it would be a linear combination of A and T in some way. So that's why you have the mask looking like this. So that is the encoder. And this is how you train it in parallel. So now we have, we have our 2 output representations here. Our patches that we have, or our byte information and our distilled byte information in these patches, where the patches are representative of the space C and A and T here, respectively. So this gives you an output sequence that looks like this, and this gives you an output sequence that looks like this. Cool. So now what you do is you send this through the transformer G. So this is, these are your tokens here. These are your patches here that you're sending through the transformer. So you take these patches and you send them through your big transformer. So this transformer here is going to be like what you would normally use in an LLM. So GPT style, just throw a ton of layers at it. This is going to be the massive transformer where all your parameters go into. And then it outputs your new representations of the tokens here, or not tokens, of the distilled representations of your bytes. I don't really want to call them patches, but of the distilled representation of the bytes. So this is just your output representation, where this has your, 2 trillion parameters, however many parameters you want to throw into this model. So normal transformer behavior. So now what we need to do is we need to decode this. So we have our patches here, but we need to decode this in some way so that we can actually make predictions. So the way you do that is by kind of inverting the decoder. So we have our encoder up here, which basically takes information from our bytes and sends it to our patches. Here, we take information from our patches and we want to send it to our bytes. So we start off with the same thing, except we take this sequence here, which is going to be our byte sequence, and we initialize it to the output of the encoder. And we take this here, which is the output of our global transformer. So instead of it being initialized to the input byte, to the original bytes and the n-gram bytes, we have the output of the encoder byte representation, and we have the output of the global transformer patch representation. We then have cross-attention. So basically, this part of the sequence isn't going to be updated at all. The patches are just sending information. They're not updated whatsoever. Like in the encoder, you had both being updated in some way. Here, you don't have it being updated at all. It's static sending information. The bytes, on the other hand, are being updated in 2 ways: cross-attention and transformers, and transformer layers. So remember I said that K and V send information to Q, so you invert this so that Q is now going to be your bytes and K and V are going to be your patches. So yeah, like I said, K and V send information to Q. Because Q creates linear combinations of basically the similarities of K and V. Anyways, so patches sending information to your bytes in this cross attention here. The norms and the no positional encodings are the same for this cross attention. Then what you have is your causal transformer layer, which is just a normal transformer layer. So this would have your self attention in it and your feed forward layer. And yeah, you just stack these blocks over and over again. Again, note that only the bytes are updated and the information from the patches are being distilled into those bytes via cross attention, via the keys and values. And then you have your outputs here. After, I don't know, 8 layers or however many you want for your decoder. So these bytes will be, or these will be your outputs, which will go into your softmax function, which you can then sample, and you can do negative log likelihood on this. So that this byte here predicts the, or rather in our original sequence, this byte here, which corresponds to the first byte, which was originally T, needs to predict H. So this will be the byte you feed into softmax to get the prediction H. Same for this byte, same for this byte, this byte, this byte, this byte. And since we did it causally, you can do this using a normal transformer training. So yeah, that was a lot. Kind of to summarize, you have some tokens here, and you have some patches. Your encoder is going to send information to these patches in some way. The patches, which are then updated, which are then distilled versions of your bytes, are going to go through a big transformer. And it'll output new representations of these patches, which are then supposed to be made to inform the bytes how to predict the next token or the next byte. So then you take these patches and they're going to update the original bytes and inform them how to predict the next token or how to predict the next byte in the sequence. Now, you can use this like a normal transformer because of that. And I have the sampling procedure, at least what I think it should be here. I looked at the code and I played around with it a little bit, and yeah, I mean, I just didn't get it working with Inference because I don't know, I just didn't. I'm gonna play around with it after. I just wanted to get this I just wanted to talk about it first because I think it's a pretty cool paper. So we have this pseudocode that I wrote here. I don't know if they had inference in the code base, actually. I didn't see like an infer.py or something like that. Anyways, they do have code, so go play around with it, see what's going on in there, because I do think this is a pretty cool engineering paper. But you can do it normally. Basically, you have your sequence, and for all the bytes you want to predict, you get your patch mask using your LLM, or rather your entropy prediction model. Remember, we have to have an entropy prediction model to have this working in the first place, and you do that on your current sequence. So that would say this here is one patch. Why do I keep doing that? Pen. This here is one patch, this here is one patch, and this here is one patch. So that would give you a patch mask that looks like 001, 01. No, that's 10011010. That would be your patch mask. You then encode and hash this. So this gives you your X, which is your encoded representation, and E, which is your n-gram encoded representation. You pull E to get your patches, your initial patch representations. That would give you your 3 tokens here, or your 3 patches. And then for your encoder blocks, you update both P and H via cross attention for P. And for H, you do that with a normal transformer layer. So it's distilling the information from H into P, which is distilling the bytes into the patches. Then you iterate over your global transformer blocks, and you take P, which are your patches, and update them. Then you send this through your decoder block, where O, which is just P, the output of your global transformer, is then distilling information to H, which is your bytes. Then you sample a new byte using this output, and you add that to your sequence. Cool. That is, yeah, that's BLT. It's a lot, though. So yeah, that's his thing. So let's look at the kind of the results they have. They have a lot of results. So I don't want to talk through all of them. Basically, the idea is that it is competitive or slightly better in most cases. So like we look at the amount of flops and we see, oh, Llama and BLT are about the same. Cool. For what is this for training? Yeah, for training. And we see that here as well. Cool. They're about the same. Nice. They also look at bits per byte estimation. So rather than looking at negative log likelihood, they look at this bits per byte because negative log likelihood only makes sense in, they say, a fixed tokenizer, as it's a measure of the uncertainty for each token. When comparing byte and token level models following previous work, we instead report bits per byte, a tokenizer independent version of perplexity. And they say where the uncertainty over the data X as measured by the sum of the cross entropy loss is normalized by the total number of bytes in X and a constant. So instead of this being the, so this is basically the like non-tokenizer version of perplexity. That's what they're kind of saying. It's a metric. So that is, yeah, that's what they mention here. They have this flops estimation if you're curious how they calculate their flops. Entropy model context, they look at the entropy model a little bit. They also say that neither of the data sets include any data generated from meta products or services. Okay, sure, they're trying to cover themselves up. No, I'm kidding. Whether they do or not, I don't really. I just think it's funny that they put it in there. Yeah, and they use this is what I was looking for, 100 million parameter entropy model with 14 layers. So it's not like it's a small model. It's somewhat large. It's still going to require a good amount on your GPU at 14 layers. And yeah. So that's some of the notes that they make over there. Scaling trends, they say it scales. They say BLT models either match or outperform their BPE counterparts, byte pair encoding, and this trend holds as we scale the model size and flops. So they have this here, and they look at some evals, and they say it's about the same as, like BLT is about the same as Llama 3, trained on a similar size and trained on a similar amount of data at a similar scale, so it's about the same. And then they say patches scale better than tokens, and they show that it does better whenever you like scale the number of tokens for Llama versus BLT. So I don't know if any of this is like actually meaningful with this benchmark stuff. I usually take all the benchmarks with a grain of salt because I don't like, they usually aren't one-to-one with how good the models are. And then they show it does different languages, like this translation. So they show it works, and they show it's not terrible. And then they show it can do well at character level tasks, which the other model couldn't. So like here, swap H and A in that. So Llama 3 can't do it because that is probably a single token. Well, it can because there's TAHT. Like this is just, I don't know, maybe you have this as a patch and this is a patch. So it can do tricks like that now. Yeah, some more notes. You need cross attention mainly in the decoder, which makes a lot of sense because it's distilling information into the output sequence. So this makes a lot of sense. The more in-gram data you add at the beginning, the better it seems to do in general. And that's about all the notes that I kind of wanted to talk about. But yeah, that is BLT, Byte Latent Transformer. I'm curious to see if this research is like, I bet you can expand upon it. Like this definitely isn't the best way to do something like this. But it's a first start, and it's a good first start. And I'm very curious to see where this goes from here. I think it has a lot of promise, like doing transformers without tokenization. I think there's a lot more work that needs to go into something like this because this is a very engineering process, heavy process. But I'm curious to see where it goes to from here.